All right, good morning, friends. So, couple of, or rather, just one announcement. The first quiz is going to happen as announced earlier on September 11, which is a Saturday from 11:30 in the morning to 1 o'clock. And the duration of the quiz is 1 hour, but like the mock quiz, I reserved 1.5 hours so that we get some time for some initial announcements or any runtime problems, if at all. Okay, syllabus is everything discussed until the last lecture, inclusive of the last lecture. Okay, all right. So let's begin.
Sir, so the quiz would start something about 10 to 15 minutes after 11:30, right?
Don't assume 10 to 15 minutes. Why? What is
Like,
the issue?
no, like sometimes like if you are just late by 1 or 2 minutes, it's not an issue, right? Like 11.
If you join late by 1 or 2 minutes, the worst that can happen is you'll miss a couple of instructions from me, if at all.
Yeah, okay, sir.
I don't think I'll tell anything new other than what has been posted already on the announcement forum.
Yeah, okay. Like so the first some few minutes you'll take for some announcements. Yeah.
Usually yes, but what is the issue, Divyanshu?
No, no, like sometimes if we get late by some time,
Acha,
it's
acha,
like it's
okay.
not an issue to panic, right? 1 or 2
Yeah,
minutes.
no, not at
Yeah,
all.
okay.
Not. Okay, good. Fine. Um, okay, so then in the last class we saw several definitions, and in this class we are going to see several proofs. But before we start with the proofs, here is a question. Rather, I want to ask two questions, but the first out of them is the following. So suppose I have a n vertex graph, okay? So and now I want to let's say I start out with the empty graph on n vertices, and now I want to add the minimum possible number of edges in order to make this a connected graph. So the question is the following: what is the minimum number of edges necessary for an n vertex graph to be connected? I hope you remember the definition of connectedness from the last time. Any ideas? Is the question clear? Right, so you're allowed to add edges in whatever way you want into the graph, but add the minimum possible number of edges and make it into a connected graph. How many edges do you need to add? Maybe I should ask a random student first. Let's say Chetan. Chetan, do you want to give it a try? Okay, Chetan is not responding. So somebody had raised their hand. Who was it?
Sir, me.
Acha, yes, Aniruddha.
Is it n-1?
Okay, so Aniruddha claims that this is n-1. So let's note this down. Why do you think so?
Because if we take one vertex and we just make n-1 edges from it to all the other vertices, then it's connected.
Then it will be connected. So which means that n-1 edges are certainly sufficient. But can you do with n-2, n-3? Is the question clear? So n-1 are good enough if you are allowed to add edges in whatever way you want. But then can you do with a fewer number of edges? Fewer edges. Anybody?
We can't, but I think
Why do you think so?
I think the proof is something related to the pigeonhole principle, but
I see.
I'll have to.
Pigeonhole principle, okay. Fine. So we'll look at the proof in today's class. But yes, the answer is correct. So the answer is correct. Good. So let us. Yeah.
So
Isha?
can't we just use induction on n?
Yeah, we'll be using induction on it. Yes, yes. Isha?
So contradiction for n-2 would be n is equal to 2. n-2
no,
and
but I'm asking, yeah, I agree. So for n equal to 2, I agree that you will require n-1, which is one edge, that I agree. But then I'm asking for a proof of the claim that for every n you will need n minus 1 edges.
So at least we cannot like go with less than n minus 1 edges. That like the base case is proving that.
So yeah, I agree that, yeah, so fine, yeah, I get your idea. Yes, so for n equal to 2, so you're claiming that there exists an n in which, for which n minus 2 edges are not going to be sufficient. So that is clear. But I want to say that for all n minus 2 edges are not sufficient. I want to make this claim. Okay? Right? So we'll prove that in today's class. So I have another question before we go into the proofs. Right? So now my question is the following. Again, you start with the empty graph. You keep on adding edges. Add as many edges as possible, but don't create a cycle. Okay? Add as many edges as you want in whatever you want, way you want, but don't create a cycle. How many edges can you add? What is the maximum number of edges that how should I say? What is the maximum number of edges in any acyclic n-vertex graph? Right. So look at all possible acyclic n-vertex graphs. What is the maximum number of edges? Yes, Ramanuj?
Again, n minus 1.
Why do you think so?
Because first of all, previously we have proven something like if there is no cycle, there are at least 2 leaf vertices, and then
Okay.
for and then I think wait, nah, this proof is incomplete. Like I was thinking something like every other vertex has 2 edges, but the answer is n minus 1. I'm pretty sure.
Okay, fine. Isha, your hand is up.
Yes, sir. So maybe we can do it by pigeonhole principle. That is, every edge has to go towards some vertex, and like we can have n, like if we have n vertices, then we will always have a collision of edges going. If we talk about directed edges for clarity.
If you have directed edges and then you have n edges, then there will always be a collision. Fine. So what? So what if there is a collision?
So it should be n minus 1 to stay connected and.
No.
Okay.
I'm talking about an acyclic graph, right? So if you want to talk of directed edges, you could have this kind of a graph also. So where there is a lot of collision, but it is an undirected graph.
Yes,
Okay.
sir.
Yeah. Viraj?
So can you use this property from the last class that if like a graph doesn't have isolated vertices and leaves, then minimum edges is n. We had proved that. So like in this, if we want to have a acyclic graph, then there must exist a leaf. At
Then
least
there
for
must exist a leaf. Good. Okay. Then what?
So then, I mean, so like it. So that's why I think I can argue that n minus 1 would be sufficient. I think. Can we do that?
I mean, you are on the right track. You took the first step in the right direction. Okay, you have the right idea probably. Maybe if I give you like another 1 hour, you should be able to write a proof. I'm pretty confident about that. Okay, good. But yes, the answer is n minus 1. Okay, and now the goal of yeah. So by the middle of today's lecture, hopefully we should be able to prove this claim. Okay. Okay. So now the right. So now I want to make the so in order to prove this claim, I want to make a certain claim which will relate all the three notions, right? The notion of being acyclic, the notion of being connected, and the notion of having n minus 1 edges. Right? So this is let's call them something. No? Let's call this property 1. Let's call this property 2. Let's call this property 3, having n minus 1 edges. Right, so what I want to claim now is that if the graph has any two out of these three properties, then the graph must also have the third property. Okay, which means the graph either doesn't have any of the three properties, or it has exactly one property out of the three, or it has all three properties. Okay, so let me make the claim. Okay, so let's go to the next slide. Maybe that's better. So the theorem is the following. Let G equal to VE be any graph with, okay, I'm getting some background noise from somebody. I don't know who. Let me just mute you all. Okay, so let G equal to VE be any graph with at least one vertex. Okay, so I'm not talking about the graph where the vertex set itself is empty. Okay, so then what? So then okay, so if any two of the following statements is true, then the remaining statement is also true. Which three statements am I talking about? First, G is connected. Second statement says G is acyclic, and the third statement says G has exactly n-1 edges. Okay, so this is a claim we'll try to prove. Okay, is the claim clear? I'm saying that if the graph is connected and acyclic, then it must have exactly n-1 edges. If the graph is connected and has exactly n-1 edges, then it must be acyclic. If the graph is acyclic and it has exactly n-1 edges, then it must be connected. Right, so pretty strong statement. Okay, so there is something on chat, maybe? No. Yeah, Arun, yes. Yeah, I just saw your reply on chat. Okay, so let's prove this. Proof. Right, so as usual, we'll use induction on n. Induction on the size of the vertex set. On the size of the vertex set. So the base case is where what base case is where size of v is equal to 1, because we have assumed that the graph contains at least one vertex. So then I'll leave this for you to verify. Left to verify. Right, so there's nothing to be done over this. G is by definition connected. G is by definition acyclic. G by definition has n-1 edges. Right, so fine. So the base case is fine. So let's worry about the inductive case. So suppose inductive case. Suppose size v is equal to n, and suppose the claim is true. The claim is true for graphs with n-1 vertices. Okay, so I'm using the plain simple induction. I'm not even using strong induction over here. So now let us prove the claim for a graph with n vertices. Okay, so let us consider the three parts one by one. So the part one is, now we want to prove, let's first prove what 1 and 2 implies 3. Let's prove. So if the graph is connected and the graph is acyclic, then the graph has exactly n-1 edges. Okay, right. So what did we see? What property of acyclic graphs did we see in the last time which you think would be helpful? I think somebody already said it. So let me ask somebody. Darshan? Okay, Darshan is not responding. somebody wants to give a starting point for this. What property of acyclic graph should we start with, right? So we are given that the graph is connected and acyclic. We saw one property of acyclic graphs in the last lecture. What was it?
So every non-empty acyclic has at least 2 leaves.
Correct. Good. So now we are given that the graph is acyclic, and obviously because it is connected and it has at least 2 vertices, it must be non-empty, right? So okay, this n is strictly greater than 1, right, for the inductive case, right? So size of V is greater than 1 and G connected. Therefore what? So G is non-empty. Okay, so further also G is acyclic. So therefore by result from last class, G has a leaf, right? So G has actually at least 2 leaves, but we are good with just 1 leaf, right? So G has a leaf, say L. Okay, so L is a leaf of G. Let's draw a diagram over here. So because L is a leaf of G, there must be a unique neighbor of L in G, right? So let us name this neighbor something, U. Let U be the unique neighbor of L. Okay, so what I'll do is the following. So how does the graph look like? So there is something happening over here. There is some graph over here, and then if you consider the vertex L, U is the unique neighbor of L. So I'll call this remaining graph as G prime, and I'll use the induction hypothesis on G prime. Okay, so let G prime be the graph given by V prime E prime, where what? So V prime is just V minus the vertex L, and E prime is E minus the set minus the edge E. Let's call this edge E, right? And yeah, maybe I should or forget it. Let's not call it E. I'll have to make a lot of changes over here. Okay, so E minus the edge UL. Right, so by induction, okay, so now how can we apply the induction hypothesis? Is G prime connected? Why is G prime connected?
So G is connected and we are only removing the leaf out of it.
Correct. So yeah, basically that is the argument, right? So right, so no path, right? So no path in G between vertices of G prime, right? So I'm saying look at any 2 vertices in G prime, which means other than L, and look at the path between them in G, right? So remember G is connected, so there is a path between them, right? So no path in G between the vertices of between any 2 vertices of G prime, between any 2 vertices of G prime passes through L. Why? Because L just has degree 1, no? Right? So therefore this path also exists. These paths also exist, maybe I should say. Right? So therefore there exists a path between every pair of vertices of G prime, right? So therefore G prime connected, right? So G prime satisfies the first property, Why is G prime acyclic? Well, removing an edge cannot create a cycle, right? So G prime is acyclic because removing edges cannot create new cycles. I hope this is clear. Right, so therefore by induction hypothesis, what do you get? So G has, what do you get by induction hypothesis? The size of, so G has exactly n minus 2 edges, right? So therefore, right, so this one edge is extra in G, sorry, G prime has exactly n minus 2 edges. So this G contains one edge extra, which is this UL edge. So therefore, G has exactly n minus 1 edges. Okay, so far so good. All right, so let us prove the next part, right? So if okay, is this part absolutely clear, right? Because if this is absolutely clear, the other two parts should be easy because we are essentially using the same idea. Any question as far as this proof is concerned? Okay, well, so even in the other two proofs, the idea is the same. Just show that the graph has a leaf, remove the leaf and the unique edge incident on it, and then use induction hypothesis on the remaining graph. Nishchay?
Hello, sir. Sir, in
Yes.
this, we are using this that G has to be both connected and acyclic for having n minus 1 edges, no?
Yes.
Okay.
I am saying that 1 and 2 implies 3.
Okay, sir.
Okay, fine. So, chalo, good. So now let's move on to the next part. Right. So I'll just copy this on the next slide and then edit wherever necessary. What is happening? Okay. So now what do we want to prove? So now let us prove that 1 and 3 implies 2. Okay. Now the idea is still going to be the same, right? So I'll just retain whatever is, yeah. Okay. Right. So ignore this part. I don't want to write it and I don't want to erase it and write it again. So which is why I just left it as it is. Right. So now again, what are we assuming? We are assuming that G is connected and G has exactly n minus 1 edges. Okay. So now, why does G have a leaf? Right. Idea is the same. Isolate a leaf in G. Why does G have a leaf? We saw some property about this graphs having at most less than n edges in the last class again, right? Vedant?
Yes, I was going to say that. So for n points, for a graph with n vertices, and for all vertices to be connected, it cannot be cyclic unless there are at least n edges.
That's what? That's what we want to prove, no? That's what we want to prove. I mean, intuitively, I'm pretty sure everybody sees it, but what is the rigorous proof?
So we cannot use that theorem.
That's exactly what we want to prove, right? Okay, yes. Chinmay?
So like if there is no isolated vertex or leaf, then it must have at least n edges.
So that's what we saw in the last class, which means if the graph has n minus 1 edges, then it must have an isolated vertex or a leaf.
Yes, sir.
But why does it now? Okay, now why does this graph G necessarily have a leaf? You're almost there, right? Why does it necessarily have a leaf?
So because it cannot have an isolated vertex, otherwise it won't be connected.
It won't be connected. Remember, the number of vertices is at least 2. Okay. right? So let's use that property. So okay, good. So since number of edges is less than n, G has an isolated vertex or a leaf, right? But since n is greater than 1 and G is connected, right? So what do we get? So G has no isolated vertex. अरे बाप रे, ये तो okay, गड़बड़ हो गया थोड़ा. So fine. Let me just move this down a bit. Okay. So, but since n is greater than 1 and G is connected, what do you get? So G does not have an isolated vertex. Right, so therefore the same idea. G has a leaf, let's say L, let U be the unique neighbor of L, let G prime be defined in the same way, V prime E prime, where you remove the vertex L and you remove the only edge incident on L. Right, so now what happens? Right, so now what do you want to say? That we want to say that G is connected, right? So with the same idea, exactly the same idea, we'll say that G prime is connected, right? So no path in G between any two vertices of G prime passes through L, right? So therefore there exists a path between every pair of vertices in G prime. So therefore G prime is connected. So far so good. Now things will change. Now things will change. What will change? So right, so this is connected, right? So we have removed one edge from G prime, so therefore, sorry, one edge from G to get G prime, and G had n minus 1 edges, so therefore G prime has n minus 2 edges, right? So size of E is equal to n minus 1, that is given to us, and therefore size of E prime is equal to n minus 2, right? So G prime is connected. The number of edges of G prime is n minus 2. So therefore, by induction hypothesis, what do you get? By induction hypothesis, you get that G prime is acyclic. Right? But now let's consider G, right? So G cannot contain a cycle because L cannot belong to any cycle. Right, so for a cycle is a closed walk of length at least 3 and in which no vertex is repeated except for the first and the last one, right? So which means every vertex that is a part of the cycle must have degree at least 2. Okay, so L cannot be a part of the cycle. I mean, otherwise if G has a cycle, then it must be a cycle in G prime also. Right, so G is acyclic. Okay, raise your hand if this was too fast. Okay, so I hope everybody got an idea of what is happening. Cool. So yes, Chinmay.
Like sir, I understand why L cannot be like a part of any cycle, but like in exams or when we are writing proof, like do we have to prove everything that we write, or if some things are implied that we can leave them? Like here.
So this level of obvious things you can leave.
Okay.
Right. Yeah, but don't leave out stuff just because you think it is obvious, right? So yeah. Okay, G cannot contain a cycle. All right, so let's move on to the third part where we will assume 2 and 3 and then prove 1, right? So we'll assume that the graph is acyclic and it has exactly n minus 1 edges, and then we'll prove that G must be connected. Idea is again the same, just isolate a leaf in the graph. So let us once again copy this entire proof and edit it wherever required. Okay, so now what? So we want to prove 2 and 3 implies 1. Right. So now again, why does G have an isolated vertex, right? Sorry, G have a leaf, right? So G is acyclic. G has exactly n minus 1 edges. Yeah, Divyanshu?
So like in these proofs, we are repeatedly using the fact that a leaf cannot belong to a cycle. So generally, like, should we start this as a lemma or a statement that we are repeatedly using?
If you are using something repeatedly and that statement needs a proof, then yeah, it's better to isolate it. It's better to separate it out as a lemma. But here it's evident, right? Cycle cannot contain a leaf vertex. I mean, it's evident from the definition of the cycle, right?
Yeah. Okay. Okay.
Yeah. So every vertex in the cycle must have degree at least 2. Okay. So therefore, I'm not writing it as a different lemma. I mean, I could do that, but that would be too boring for you all. I'm pretty sure. Okay, trying to prove obvious things, extremely obvious things. I mean, all these are also kind of obvious, but okay, the point is you should be able to rigorously prove these things. Okay, fine. So now why does G have a leaf vertex? Any argument for that? Again, use the properties from last class, right? So let me ask some random student. Gunjan. Gunjan is not responding. Somebody? Anybody?
Well, like it is acyclic, so it has at least 2 edges.
Acyclic, and then more importantly, just for completeness, you also need to mention that why is G non-empty, right? So
like
n is greater
minus
than 1, and it has n minus 1 edges, right? So which means it has at least 1 edge, and therefore it is non-empty. Good, fine, right? So so n is greater than 1, and G has n minus 1 edges. So therefore G non-empty. So moreover, G acyclic. So therefore using by result from last class, what do you get? G has a leaf, say L. Okay, then the next few statements are the same. Let be you be the unique neighbor, construct the graph G prime as before, no change over here. Now the changes will start happening from here, right? Okay, what do we have? G is acyclic. Okay, now we want to prove that. Okay, so changes will start happening from here. Okay, now what do we want to prove? We want to prove that G prime is acyclic and G prime has exactly n minus 2 edges. Out of them, one is evident, right? So size of E prime is size of E minus 1, which is equal to n minus 2, right? We are given that size of E is n minus 1. Right, so this part is clear. Why is G acyclic? So removing edges cannot create cycle. right? So therefore G prime is acyclic, right? We assume that G is acyclic, right? 2 and 3 implies 1. Okay, so G prime is acyclic. The number of edges of G prime is 1 less than the number of vertices. So therefore G prime is connected. Okay, so now for any two vertices, let's call them AB, right? So AB both not equal to L. G prime contains a path, contains an A to B path. So therefore G also contains an A to B path. We are only adding edges, right? So paths cannot be destroyed. G contains an A to B path for a vertex A not equal to L. What else do we want to prove? We want to prove that there is an A to L path in G, right? So appending for a vertex A not equal to L, G prime contains an A to U path. Okay, appending L to this path gives an A to L path, right? So what are we trying to prove? We are trying to prove that G is connected, right? So we want to prove that G contains a path between every pair of vertices. So if those two vertices are other than L, then G prime itself already contains a path. So there is nothing to prove. Otherwise, if one of them is L, right? So we'll use the path from the other vertex to U and then just append L to it. Okay, so apparently there is something on chat. Achha, okay, no issues, Gunjan, it's okay. Okay, is this fine? Is this fine? Is this absolutely clear? Raise your hand if anything is not clear. Okay, Manthan.
Sir, at first we write 3 claim in the question. Are we trying to prove that these 3 are equivalent?
No. The meaning of equivalent is different, right? Equivalent means if one of them is true, then all three are true.
Okay, so we have to first assume that any of the 3 is true. Then using this, we try to figure out other 2.
That would be the meaning of equivalent statements, but that's not what I'm claiming over here. It is possible that one of them is true and the other 2 are false. All I am saying is if 2 are true, then the third must also be true.
Okay, sir.
Okay, so is this difference absolutely clear to everybody else in the class? Right? When you say a set of statements, some 10 statements is equivalent, it means that as soon as one of them is true, everything else is true. That's not what we are seeing over here. You can have a graph which is connected, but neither acyclic nor it has n-1 edges. You can have a graph which is acyclic, but it is not connected and it does not have n-1 edges. And you can have graphs which have n-1 edges, but which are neither connected nor acyclic. All we are seeing over here is if 2 of the 3 properties are satisfied, then even the third property is satisfied. Okay. So now we'll give a nice name to the graphs which satisfy any 2 or equivalently all 3 properties. Okay, we'll call them trees, and that is for the evident reason, for the obvious reason of that. Okay, so basically they really appear like trees, which is why we'll call them trees. Okay, right. So definition. A graph G equal to VE is called a tree if it satisfies any 2 or equivalently all 3 of the following properties. Following properties, or let me say, if any two or equivalently all three of the following statements are true. Okay, what three statements? G is connected. Second statement, G is acyclic. And third statement, the number of edges is equal to the number of vertices minus 1. Okay, so we just proved that if any two of these three statements is true, then the third is also true. So therefore, if a graph satisfies any two or equivalently all three of these statements, then we'll call it a tree. Okay, so which means if you want to prove that some graph is a tree, it's actually sufficient to show any two of these three conditions is true. Rishabh?
Sir, I had a short proof of 2 and 3 implies 1, so I just want to know if there's any.
2 and 3 implies 1. Okay, go on. Yes.
Yeah. So basically, suppose it has k connected components, and if k is equal to 1, you're done. So
yeah.
So if k is greater than 1, each connected component has less than n elements.
Okay.
So inductively from 1, no, actually you don't need induction. So say 1, so from 1 and 2 implies 3, you get that each of these has ni minus 1 edges, where ni is the number of elements.
I see. For the
and then you just sum it all up.
So for the connected components, you are using the first out of the three claims in the induction hypothesis instead of the third. Sounds good.
No,
Sounds
you actually don't need induction at all. Yeah. So my only question was, do we say have to prove that you can partition the graph into connected components first, or?
That is also fine. The way you stated the proof, that is also looks reasonable to me. That's not what I have done though.
Yeah.
Okay.
Yeah. So I just wanted to know if there's like any thing here I need to take it off.
Sounds like a reasonable idea. That sounds like a reasonable idea.
Yeah, okay. Thank you.
Yeah, but remember, because we are proving the claim that two of the three statements implies the third, and you are proving this claim using induction, which is why your proof is a valid proof. If you are just trying to prove that 2 and 3 implies 1, you are just trying to prove this claim using induction, then you will have to first prove the other claim which you are using as a part of your proof, right?
So yeah, actually, if you first prove the first claim and then use it, I don't think you need induction.
Sounds
for
good.
Using the first claim actually.
Okay, sounds good. Okay, fine. Right, so yeah, so this is a tree. I don't know how will a tree typically look like, right? It will be something like this. Right, a tree graph is going to look something like this. Okay. Okay. By the way, I need to mention that when a graph is acyclic, you also call it a forest. So let me just mention it over here. So G is acyclic, also known as a forest. Right? They are the same thing. Isha?
So I wanted to understand that the argument using connected components for 2 and 3 implies 1. So isn't it using strong induction?
It is using strong. Yes, it is using strong induction. Yes, you're right.
Okay.
Yeah. Okay, so now as an exercise, what you could prove, I'll add this as in the tutorial problem set. So claim the number of connected components in the graph G equal to VE is at least, any guess what how should I complete the statement? Isha, your hand is up. Do you want to answer?
No, sir, it's my mistake.
N minus number of edges.
N minus number of edges, which means you are trying to say the number of vertices minus the number of edges. Is that what you are trying to say?
Oh, yes.
So yes, this is the claim. Okay, so it should be reasonably easy to prove. So this is this for the tutorial. Okay. Okay, so now I want to ask two questions about concerning trees, right? So suppose I take a tree graph, and I remove one of the edges of the tree graph. Okay, what kind of a graph will I get? Any obvious answer? All right, so question is the following. Suppose G equal to VE is a tree and E is some edge in capital E, right? So how does the graph G prime equal to V and E minus E look like? Yeah, Divyanshu?
It would be like two different trees, two disconnected trees.
Two disconnected trees. Necessarily two disconnected trees? Is it clear that it has to be exactly two disconnected trees and not? First of all, is it clear that the graph must get disconnected? I mean, from this diagram, it should be
clear. We prove that if from a given vertex to another vertex, there is a unique path in a tree.
So that needs a proof. Yes. The statement is true, but that needs a proof. And once you prove that, then maybe you can say, okay, it gets disconnected into two parts and so on.
Yeah.
Okay. Right. So yes, you have the right idea in your mind, and we are going to prove it via that way itself. But then I have another question, so let me also put it. Now let's do the following. So suppose we again have a tree. Suppose there's a tree and okay, I'm getting background noise from somebody. I don't know who. Okay, and now in this case, E is not an edge of G. Okay, so E is a subset of V of size 2 such that E is not in the edge set. Okay, so how does the graph right? What am I doing now? I am taking the same vertex set, but I am adding the edge, adding E as an edge to the edge set. Like Isha?
This graph will now have a cycle from the previous claim.
From which claim?
Like the one which we were proving earlier, like the two statements.
Because yeah, you mean to say it is still connected. So if the first property is not violated, so which means that if one of the other two properties is violated, then the third property must also be violated. Yeah. Right? That's what that's the way you're using it.
Yeah.
Yes, so it must contain a cycle. That is true. But will it? How many cycles? Can it contain more than one cycle? Can it contain, I don't know, 5 cycles? How many cycles will get created? Okay.
One cycle.
Only one.
Only one.
Why?
Because if it is going to contain 2 cycles by only adding one edges, then there must be a previous cycle and the edges must be part of the inside the cycle. I mean,
What do you mean?
What?
Right. So if addition of this edge creates two cycles, right? So they could be intersecting. I don't know. I don't care. Fine. So then what?
Then by removing the edges, there must be a cycle existing. I mean,
But again, that needs a proof, right? So if I remove this edge, you should be able to find the cycle in this remaining graph. That kind of needs a proof, right? Because what is left might not be a cycle; it might just be a closed loop, no? Right? Do you get my point?
yes, sir.
You traverse this cycle up to this point, and then you traverse the other cycle in the backward direction. What you'll get is a closed loop. Why is it a cycle? I mean, in general, it is not going to be a cycle, but then you want to claim that there is a cycle in the graph. Sachit?
So why should E belongs to E, capital E?
What are you talking about? This part?
Like in the question, such that E belongs to capital E, small e belongs to capital E.
In the first question, right?
No, in the second question.
So that should be E doesn't belong to E, otherwise the union won't change.
Sorry.
Sir, like in the like somebody said that using the previous results we can prove it. I didn't get that. Like if one will be true, statement 3 will become false. So does that imply 2 will also become false?
Sorry, say that again.
So like somebody said that using the previous results, the state point number 1 will remain true, 3 will become false. So that will imply 2 will become false. Like
exactly, because that's by contrapositive, no? If 2 itself is true, then 1 and 2 is true, so therefore 3 must be true. That is a contradiction.
Oh,
okay. So so just keep this in mind that either 0 of these statements are true, or one of the statements is true, or all 3 are true. It cannot be the case that 2 are true and 1 is false.
Got it.
Yeah. Okay. Good. So so this needs a proof, and again it relies on the fact that as soon as you have two paths from one vertex to other, two paths between some two vertices, then the graph must contain a cycle. Okay, so that is the claim that we'll try to prove now. Okay, so the claim we'll prove is fine, we have time. Claim. Okay. A graph G has a cycle if and only if what? There exist two vertices A and B. Okay, let me give a name to the vertex set and edge set. There exist two vertices A equal to A and B in V, two distinct vertices. Distinct vertices A and B in V such that G contains at least two paths from A to B. Okay, so this is an if and only if claim. If G contains a cycle, then you must be able to find two vertices which have at least two paths. And conversely, if there are two vertices which have at least two paths, you must be able to find the cycle in G. Okay, so one direction of the claim is obvious. Which one is it? Which is the easier direction to prove?
So like if there are two parts, then we can like kind of join them and then reduce them to get a cycle.
Join them, reduce them to the get a cycle. That's quite non-trivial, right? What about the other part?
If there's a cycle, then you'll have two paths already.
Exactly. That's the easy part, right? So right, so this is the easy direction. Forward implication is the easy direction, right? So suppose what? Suppose V0, V1, V2, Vm minus 1, V0 is a cycle. Right, so then by definition m must be at least right, so m must be at least what, 2, no? Okay, actually let me just rename it. Let's not get confused. Let me call the cycle v1, v2, vm, v1. Okay, so then m must be at least 3, right? So that is by definition, right? The length of the cycle must be at least 3. Okay, so then therefore what? So it means that right, so therefore v1, v2 and what? So v1, vm minus 1, v2 are 2 different paths from v1 to v2 in G. Okay, so in effect this is a proof by construction in some sense, right? So there is a cycle in the graph. Let's just look at 2 vertices in the cycle, 2 consecutive vertices in the cycle. There is a direct edge that gives one path and the remaining cycle gives another path. And because the length of the cycle is at least 3, by definition, these are 2 distinct paths, right? So this would not be valid if you are talking about this kind of a closed walk, right? So then this would give just one path between the two. Okay, so now what about the other way?
Sir, in the other case, we can just construct the cycle because if we know there exists at least 2 different paths. So V1, suppose first path is V1, V2 between V1 and V1 dash, and so till Vn and V2.
I am not sure how you are naming
sir,
them. So
there are 2 paths between. Okay, sir, you can name it anyway, like V1 to Vm.
Let's call them X, V1, V2, some Vk, Y, and P2 is the path X, U1. Why am I not able to write? Let's say the other path is X, W1, W2 up to some WL and again Y. So then what?
Yes, sir. So now we can construct a cycle because since all individually V1 and Vk all are distinct, and here W1 and WL are all distinct. Then we can construct a cycle X, V1, V2, Vk, Y, WL, WL minus 1 to W1, X.
Is this necessarily a cycle?
No, sir. Some might collide. Means some might be equal, like Vi and Wj.
So some Vi might be equal to some Wj, no? Right, Ramanuj?
Okay.
So in this, first of all, is L equal to K for sure, right? Because both are paths.
Why is L equal to K?
I mean, wasn't path defined as the minimum distance thing, so both should be equal.
No, I just defined the paths to be a sequence of vertices so that the consecutive vertices are adjacent. That's all, right?
Okay.
Right.
So anyways, we can do this.
I can take this as A and there are 2 paths from A to B. Yeah. Okay. How do you do it?
So anyways, we can do this like for V1, V2, and W1, W2 ... We choose Vi and Wi such that it is the first place where Vi is not equal to Wi, and then similarly we do it from the end, and then we can make it's Vi, Wi, and Vj, Wj. Then we can make Vi minus 1 till Vj plus 1, and then from that we can do
Ramanuj, could you tell it from the beginning once again? So you have these 2 paths. What do you do? I didn't follow.
So we choose the first element in Vi such that Vi is not equal to Wi.
First element and not equal to.
Yeah, so the first element in first place where they differ from each other.
So let's say V1 itself is the first place. Then what?
Then also we choose the last place where they differ.
Let's say Vk is also the last place where they differ. Okay, then what?
So then then one before that and one after that, like those will be the same.
Why? This could also be different. No? You're talking about the early place where they differ, no?
Yeah, so the one place before the earliest place they differ will be the same.
No, I'm saying V1 itself is the first place where they differ. How does your proof go in this case?
Yeah, so if it's V1, then choose X. Like X is also part of the sequence. X
okay. So then what do you do?
And also choose the element which is one after the last place.
So that is Y in this case. Then what?
Then you can construct in this case X, V1, V2, Vk, Y, and then W1, W2, and to W1.
But that's the problem, right? So this is my path. This is my first path. Okay, so we draw it properly. So this is my first path, right? So this is my X, this is my Y, this is the blue one is the path P1, and this is the second path.
Okay, so instead of the last one, you have to choose the next one which differs. Like first you choose an element which is the first element which differs, and then you choose the next element which is.
Do you think that your proof is going to cover all cases? I'm doubtful about that.
So like we can just choose either all of them will be different.
One sec. Ramanuj, if you think you have a proof, just write it down and share it with us. Okay? If you think your idea is promising, then just write down the proof and share it with us. Prabal?
Sir, excuse me, sir.
Yeah.
Sir,
okay.
In Nishya's idea.
Okay, right, Prabal, go.
Okay,
sorry.
thanks. In Nishya's idea, you said that what if a Vi collides with Wj?
Right. WG, that is the question.
So,
yes.
sir, in that case, that would also make a cycle from Vi to Wj.
Correct. But then what if there is another collision over there?
Sir, so we will use the well ordering property.
Exactly. Very nice. Exactly. Very nice. Well ordering on what? Just tell the details now. You have the right idea. Well ordering on what? What set?
Sir, the set of Vi and Wj that collides.
Acha.
Sir, I can there's better way to put it, I think.
Okay. What is the better way to put it?
We are considering set V1, Vk up till Y and W1, Wl up till Y. So we'll consider the first element which is same. There will be some element because Y is same. So
wait, so first element in P1 which is same as some W, the earliest Vi which is same as some Wj, or the earliest Wj which is same as some Wi? Or does it not matter?
In both cases, the earliest.
ऐसा नहीं हो सकता ना. There might be so W5 might be same as V10 and V7 might be same as W15. No, what do you do in this case? So these two might be the same and these two might be the same.
So we will use that well ordering X, Y I define in the GCD proof. We can use that.
GCD proof. What does that have to do with
lexicographically?
We can then I think we can take any then. Like for example, you are going in V and
we can take any. Okay, okay, sounds good. And, yeah, so that sounds like a promising idea. Yes, I agree. Other people, Somil?
So I think Ramanuj's idea can be fixed. Like the initial part is same. Like you take V1, V2 and W1, W2 and take the first I such that Vi is not equal to Wi, which will happen because otherwise the paths will be same. So then what you do is you disconnect you remove the edge Vi minus 1 Vi and Wi minus 1 Wi. And then you notice that you still have a walk from Vi to Wi because you go from Vi to Y and then go from Y to Wi. So even after removing the edges Vi minus 1 Vi and Wi minus 1 Wi, you have a walk. So there's a path in this subgraph. So then if you join this path with the path Wi Vi minus 1 Vi, then you get a cycle.
Oh, I see. I get, yeah, I get the idea. I'll be very interested in reading the concrete proof. So just write it down and share it. Okay. Yeah, the idea is promising.
The one I had before, like a bit cleaner, but like a bit different, I think.
Okay.
I just write.
Isha, your hand is up.
So maybe we can prove it by contrapositive. That is, we can say that so G is acyclic. So if G is acyclic, then G must. So every vertex should have at least. So there should be one path or zero paths between any two vertices.
At most one path. Okay, how do you prove it now?
So that can be proved.
Wait. You're proving. Acha. So instead of the second statement implying the first statement, you are saying, okay, negation of the first statement implies the second. Okay, good. Yeah, go on. Yes. How?
So we can prove it by the fact that if G is acyclic, then we must have at least two leaves or an isolated vertex.
Okay.
So like we can like if we talk about the leaf, so the leaf will have one path only to any of the vertices because
Fine.
it has only one degree. Like the degree is one.
I completely disagree. Right. So the leaf has just one edge. Agreed. But then beyond this edge, it could have several paths. No.
Yes, sir.
Okay. Yeah.
But then they should be two different vertices. Like for one vertex, we should have only one path. Otherwise, we'll have a circle.
That's what you want to prove, no?
You
are assuming that the graph is acyclic.
Yes.
Okay, Somil, your hand is up once again. Yes.
So can we induct in this case, like basically like Isha's idea? So what you do is you take the acyclic graph and you say you have a leaf.
It's a leaf, let's say, okay.
Then you first consider the paths with consider the pairs of vertices other than the leaf, like both the vertices are other than the leaf. Then then we already saw that a path between those two vertices cannot involve the leaf. So we can just remove the leaf edge, like the edge connecting the leaf to the graph, and we can use the induction hypothesis to say that these vertices will have only a unique path, and then to prove that a leaf and another vertex will have a unique path, you see that any path from the leaf to another vertex will have first the leaf L.
You have that idea, yes. Yeah, so the first vertex must be U. And then there's a unique path between you and every other vertex, no?
Yes.
At most one path between you and every other vertex. Yes, that seems like a nice idea. Very good. Okay, yeah, write it down and share it with us. Sounds good. Okay, so let me go with, I forgot the name now. I don't know, Manthan or whoever. Yeah. So,
What's up?
No. I think somebody had given the idea. I thought it was you, but maybe not. I'm not sure. Okay. So let me say out my own idea, right? So maybe another way to prove the same thing, right? So I'm going to look at the following set, right? So let L len of P denote the length of a path P. Of a path P. Okay, so consider the set. Consider the set len of P plus len of P prime such that P and P prime are paths in G with the same endpoints. right? So I'm going over all possible paths in G, all pairs of paths in G which have the same endpoints. And then I'm just putting the sum of their lengths into this set. Okay. So since there exist two vertices A and B such that G contains a path, G contains at least two paths from A to B, this set is non-empty. Okay. So did somebody post something on chat? Achha, no. Okay. Yeah. So right. So we are given. Let's call this set something S. We are given that S is not empty. Right? We are given that there exist two vertices for which there are some two paths. Okay. So by well ordering principle, S has a minimum. Remember, S is a set of integers. Okay. So non-negative integers. So S has a minimum element, say okay, yeah, say M, right? So therefore there exist vertices, let's say X and Y, and paths P1 P2 from X to Y of total length M. Right? So this is just by the definition of the set S. Right? So let those paths be exactly these, right? So right, so where what? So the lengths, the total of the two lengths is M, no? So which means K plus L plus 2 is equal to M. Okay, so now what? So now we know V1 through Vk are all distinct and different from X and Y. Similarly, W1 through WL are all distinct and different from X and Y by definition of the path. Okay, so now what do we want to claim? We actually want to claim that all these are distinct, right? So we want to claim that no Vi is equal to any Wj, right? So we want to claim that yeah. So let me erase this and create some space over here. The idea is exactly the same. Right. So if there exists Ij such that let's say Vi equal to Wj, and let's also give this vertex some name, let's say Z, then what? P1 prime, which is equal to X V1 V2 up to Vi minus 1, and then Z, and P2 prime, which is equal to X W1 W2 Wj minus 1 followed by Z, are two paths between the same pair of vertices X and Z of total length Total length what? What is the total length of this? It is definitely less than m, no? Total length less than m. So this is a contradiction too. This contradicts the minimality of m. Right, so therefore what do you have? Therefore we have that x, y, v1 through vk and what, w1 through wl are all distinct vertices. Right, and because all these are distinct vertices, so therefore what, x, v1, v2, blah blah blah, vk followed by y and wl minus 1, w1, x. So this is a cycle. Yeah, Rishabh?
Sir, do we have to take special care of the case where I is equal to j is equal to 1?
I is equal to j is equal to 1. We don't, right? Because
we can shift x to the one.
Both of them become xz and xz.
Then we can see.
I is equal. Acha. Oh, I see what you are saying. Yeah. Good. So how do we take care of it? Then we'll have to do something with that vertex and y, no?
So can't we just shift the x to that place? I mean,
that's what I meant. So you look at what happens between that vertex and y.
Yeah.
Good. And then if yeah, makes sense. And now if you land up in the same problem where
then you get two equal paths. So
then you get two equal paths. Yes. Very nice. Good. So let me just note it down over here and leave it as an exercise, because that seems like it follows from the same idea, right? Okay, so what if I is equal to j is equal to 1? Complete the proof. Okay, should I leave this for you to complete? Raise your hand if you are not comfortable completing this proof. Ramanuj, you have a question, or you are not sure whether you'll be able to complete the proof? You'll be able to.
No, sir. I had a proof. I just wrote it out in LaTeX. So I think it's like very similar to this, but it's written.
Where did you write it?
I just wrote it out. I'm just sending it. I'm joined from my phone. Wait. I'll just send it to someone.
It's okay. No, there is no hurry. You can send it around. Say it's not a big issue.
So, like, could you repeat?
Sir, if I equal to j equal to 1, it means that both P1 and P2 are same, but we are given that there are at least two paths from E to C.
No. I equal to j equal to 1, but the V2 to Vi minus 1 could be different from W2 to Wj minus 1. That's the point. Right? So which is why you have two different paths. Okay?
So could you once repeat it?
Sorry?
So like if I and j both are equal, it means that V1 equal to W1 equal to Z.
No, what? V1 equal to W1 equal to Z. Yeah, so then P1 prime and P2 prime are just the same path. That is the problem. Okay?
Yes,
yeah. So which is why you won't be able to say that their total length must be in S. Okay, Dhruv?
So I was saying that if I is equal to j is equal to 1, then we can take x dash is equal to v1 is equal to w1.
Correct. And proceed as before. Yes, that is precisely the idea. So it's just a matter of completing the proof. Because I've left it incomplete, I've said that okay, you should complete the proof.
So like
and
in
then
this
after
case, we'll have
after
to do it again and again, right?
Sorry.
So actually,
like for
No,
example, then V2 can be become to W2. Then we'll have to use like well ordering.
Yeah, exactly. Use well ordering. Don't do it again and again.
Okay.
So I think there's like a more general issue. If I is equal to J and then V1 is equal to W1, V2 is equal to W2, and so on, then you again have issues.
No. See, if I equal to J equal to 1, what you can say is look at the first vertex V1, W1, and then look at the vertex Y.
So I meant if I is equal to J, not necessarily equal to 1, and
Okay.
V1 and W1 are equal, V2 and W2 are equal, and so on, then you again get the same path. And that doesn't contradict anything.
No, that's what I'm saying. That's still not a big issue. That's still not at all an issue, because as soon as you say as soon as you have V1 equal to W1, what I'll do is I'll take this as one vertex and Y as the other vertex. And now look, I have two different paths between the same pair of vertices. That will contradict my choice of S, a choice of M. So
Yeah, it's easily fixable, but I think it's as big of a thing as the equal to 1 case.
So the only case we need to worry about is where K and L are both 1 and I and J are also both 1. And then in that case, the answer is trivial because it's just the same path. Okay. So that is the only corner case where you need some different argument. K, L, I, J are all 1.
Yeah, that's the only case you need different argument, but I think you need to separately consider the case where the paths P1 dash and P2 dash are the same, which is possible in cases other than where I and J are 1.
What cases is that possible? Assuming P1 and P2 are different, can you start P1 prime and P2 prime?
So you have like say path P1 is a path between 1 to 2, 2 to 3, and 3 to 4, and like 4 to 5, and then P2 is 1 to 2, 2 to 3, 3 to 6, and 6 to 5. Then if you consider the third vertex in both of these as your IJ,
3 to 6 and 6 to 5, okay?
Yes. So if you take 3 to be your Vi and Wj, then again you only have the path 1, 2, 3 for P1 dash and P2 dash.
I see what. Okay, I see.
What is he saying? What is he claiming?
Oh, I see. So I get your point. Okay. Yeah. So this is missing. This is a missing argument from my proof. Yes. So this is your X. This is your Y, and this is your Vi equal to Wj. Let's say. Right, and then so these two, we started out with two different paths, but now what we are getting out of this is this P1 and P2 are the same path. Right, so that is a flaw in the argument. That is indeed a flaw in the argument.
We can correct it by just considering that Vi is never V1 is never equal to W1, because if it is, then we can just consider starting from there.
There is an easy fix. What I'll do is right. So I know Vi is equal to Wj. So I'll look at these four paths instead, right? So I don't think I'll be able to finish this. Maybe in the next lecture I'll formally do it once again, right? So but the idea is to look at these four paths: X, V1, V2 up to Vi, right? So let's call this Z. So this is just Z. X, W1, W2 up to Wj minus 1 Z, and then I'll also look at these other two paths: Z, Vi plus 1 up to Y and Z, Wj plus 1 up to Y. Right. So if these two paths are distinct, then we contradict the choice of M. If these two are distinct, then we contradict the choice of M once again. But if these two are the same and these two are the same, then the original paths must be the same.
Sir. Sir, we can also fix this issue by, suppose in the claim itself we can write where we are choosing the paths, we can just say that W1 and V1 has to be different. If they are same, then we just shift X to W1 or V1.
So that's what you're doing over here, no? If V1 and W1 is the same,
so we don't have to check for the other one. No, we are sure that they will then diverge. Like it will have two different paths.
essentially it appears to me that it's essentially the same argument, no? I mean, in our case, so basically if V1 is W1, then these two paths will be XZ, XZ, and you will have Z blah 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 Y, Z blah 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 Y. Right? And the same argument will follow. If these two are distinct, which they are not, you'll contradict the choice of M. If these two are distinct, if you'll contradict the choice of M. If these two are the same, which they are actually, and these two are the same, then you have that P1 is the same as P2.
Yes.
Which
sir.
is a contradiction. Yeah.
Right.
Okay.
So
Yeah.
which is pretty small. Can you look at it? It's in the chat, I think.
Oh, what is it?
It's a proof which is, I think, a bit similar to this, but it's like it's in the chat. It's pretty small.
Okay. Consider the first element in the set V1 through VK Y Vi such that Vi is in. Acha, we know fine. Okay. We can see Vi is equal to Wj for some j. Good. Now we claim x2 Vi minus 1 Wj to W1 has every element distinct because Vi does not belong to that set, which is fine. I guess you meant Vi does not belong to the set W1 through Wj plus 1 or something, or j minus 1, I don't know.
It belonging to L plus 1 till the end because it doesn't belong to the previously given set. So it belong to
that sounds reasonable. That looks good to me. That also looks good to me. Yes. Okay. Yeah. So I agree that there is a little flaw in this proof. So we'll revisit this proof in the next class, and then we'll fix the issue. Okay. But yeah, sounds good. Any questions before we close?
Isn't this proof too long? I mean,
Which proof is too long?
So this two parts from A to B imply that G has a cycle.
No, which proof? The one in the chat or the one which I'm presenting?
The one you are presenting. The chat one is.
Maybe it's a bit too long. Maybe the one in the chat is shorter.
Yes, sir. That's what.
Yeah, I agree. Maybe that is simple. Yeah.
Here, P and P dash that we define in the set S, len P plus len P dash, then they should be distinct, right?
Sorry?
They should be different paths, right? P and P dash.
Are distinct. Maybe I should add that. Distinct paths. Yeah, that's what I mean. Okay, fine. Any other questions? Time is almost up. All right, so yeah, time is up. Chalo, so we'll meet each other on Monday at the usual time. Chalo, see you.